Hello everybody. Today we're going to learn a little bit about bonding and naming of molecules. And I call this the quick guide to bonding and naming, and that's honestly a little bit of a joke because bonding and naming gets really complicated really fast. So we're going to try to focus on the patterns as always. We're going to focus on some of the common exceptions this time so that we're able to name a bigger variety of things. You will need to look at your reader in your reference section, and you will need to do the practice problems on the worksheets because you really need some exposure to the finer details and examples and the patterns and things like that. So make sure that you aren't only relying on this PowerPoint. This is kind of a good starting place, but you do need to look at those other documents to really have a better full picture of how we do this. Okay, so first let's just think about for a moment, like, why do bonds even form? Why do atoms even bond together? And the reason is because it's going to lower the potential energy between the particles, and the bond is going to form when that potential energy is at its lowest point. And kind of a more everyday way to explain that is by saying that it's what happens when they're the most stable. They're going to bond at the point at which they're the most stable. Okay, this potential energy graph is almost always going to have the very same shape you see here. Okay, it may be a little bit shorter, it may be spread out a little bit longer, but it will always kind of start up high and come down and reach a low point, and then it's going to kind of come back up and trail off like that. Look at the pictures at the top. Okay, over here on the right, we have two atoms that are completely all by themselves. They are not bonded at all. They're just next to each other. Okay, and they have their potential energy like this. As they get closer and closer, their orbitals start to overlap. Okay, they start to share electrons. They start to maybe get closer and closer to bonding. They're getting more and more stable. Their potential energy is getting lower and lower and lower. And they finally reach this valley down here, this low point. At this low point, this amount of energy is what we call the bond energy. This is the lowest potential energy they can have. It's their most stable positioning. You can see here the orbitals are overlapping, and whatever this distance is at its most stable point, the distance between the nuclei, we say is the bond length. So if you have numbers down here on your x-axis, you can come down to the lowest point and see how long the bond is. Or if you want to know how strong the bond is, you can see where the bond energy would be. Okay? I don't expect you to know, what this would look like or the numbers for any particular atoms. If I give you a graph, I do expect you to be able to explain it or to be able to show me what the bond length or the bond energy is by using the graph. Couple of types of bonds. We typically learn this in middle school. We will probably learn a little bit more detail. Ionic bonds are when electrons are transferred. For example, sodium is going to give away its electron. That causes it to be a plus charge, a cation, and the chlorine becomes an anion. Once they are in ion form, then they are electrostatically attracted to each other, and that attraction is that bond, okay? So the electrostatic bond between a positive and a negative charge is what we call an ionic bond. Typically, they're going to be a metal and a non-metal. Metals like to make cations, non-metals like to make anions. Metals like to give away electrons, non-metals like to gain electrons. It's a perfect pair. There is an exception. We can have polyatomic ions that can bond as long as you have a cation and an anion. You do need to have a plus and a minus charge, okay? and then they'll be able to have that electrostatic attraction. A covalent bond is what happens when they're not going to fully transfer. They can't, make it happen all the way. So what they're going to do is they're going to end up compromising and they're going to end up sharing because that's better than nothing. Covalent bonds are going to typically be between nonmetals and nonmetals. Remember that hydrogen is a nonmetal. Even though it's on the left, it's a nonmetal. You can see here that the carbon is sharing one of its electrons and the hydrogen is sharing one of its electrons. And so it forms a bond where they're being shared. Okay. The reason they cannot fully transfer the electrons is in order for them to be transferred, you have to have a sufficiently low ionization energy on one atom and a really high electronegativity on the other. It needs to be very easy to take away an electron, and the atom needs to be very strong in order to yank it off of the first atom. So nonmetals are not going to be a good combo of ionization and electronegativity. So it's not going to be easy to totally remove an electron. So instead they just share. Metallic bonds are a little strange because what ends up happening is the electrons kind of detach from the atoms they came from and they end up flowing all over the place randomly. They just kind of are bouncing around in between all over the place, and what ends up happening is it's like they don't really belong to an atom anymore. They kind of belong to this collective, arrangement of atoms, and what we do is we call that delocalized. Okay, rather than being, attached to this atom, they're zooming around all over the place. And we call that a sea of electrons sometimes. If you imagine a river flows in one direction, right? Whereas the sea, the ocean, the water is kind of milling around all over the place. So that's why we call it a sea of electrons. This is what allows the metal to conduct electricity. If you apply a charge to the ends of a piece of metal, you can cause the electrons to all stop what they're doing and go in one direction. So you can, when you have the light switch off, you flick it on, the electrons are all going to stop and they're all going to start flowing in the same direction. And that's the electricity flowing through the wire and then flowing through the light bulb, right? So it's this delocalized electrons, these detached electrons, that is very important to a metallic bond because that's one of its distinguishing characteristics. Okay, just a reminder, we should know this, but I just want to make sure we don't forget that a cation is positive and an anion is negative. We can have monoatomic or polyatomic. A monoatomic ion is just one type of element, right? You got magnesium or you got sodium, for example. Polyatomic is what happens when you have two or more elements that are covalently bonded to each other, but their little package comes with a negative charge, or it comes with a positive charge. So right here, this is cyanide, okay? So carbon and nitrogen are covalently bonded. They're sharing electrons, but their overall package here has an extra electron compared to the number of protons. So they travel around bonded together, but they function like an ion. This right here is called sulfate. You have sulfur and 4 oxygens bonded together, but there's a couple extra electrons, and so they travel together as a package, and they function like an ion. Your polyatomic ions, you have some that you need to memorize. They are on your common ion sheet in your reference section of your binder, so please make sure you start memorizing them. It is the equivalent to an English class saying, okay, I need you to write a 10-page essay. in class and you have, I don't know, 2 hours to do it. I don't know if that's even doable, but let's just pretend, okay? So if you don't even know your alphabet and you have to look up in the dictionary how to spell every single word for a 10-page essay, is there any chance you're going to finish that in time? No. And the same is true in chemistry. If you don't know your ions and you have to look them up every single time, you are never going to finish anything. You are going to run out of time every time. Okay? So you have to memorize some of these polyatomic ions so that your alphabet is big enough and memorized enough that you can put them together to form molecules. Then you can put molecules together to form reactions. If you have to look it up every time, just like that English essay, you're not going to finish. Okay? So please, please, please memorize those ions. I personally would be willing to bet that one of the number one causes of people to struggle, especially second semester, is that they didn't learn their ions. And it's not that they're hard, it's that it takes time. You're memorizing something, and that takes effort. And if you don't put the effort in, it's not going to happen. And it's going to make you struggle for the rest of the year. So I'm begging you to learn your ions. Dimensional analysis and ions are the two most important things to get you through to the end of the year. Okay? Let's look at some of these monoatomic ions and figure out, how do I know magnesium's a +2 and how do I know that sodium's a +1? The nice thing with these is that it's going to be based on location. There's a pattern we can use. Everything in this first column would like to lose 1 electron. If lithium loses an electron, it will look like helium. If sodium loses an electron, it will look like neon. So by losing 1 electron, they're going to reach a stable configuration of a noble gas. So everything here likes to make a +1. Group 2 likes to make a +2. If magnesium loses 2, it's going to look like neon. If calcium loses 2, it's going to look like argon. So everything in group 2 makes a +2 ion. Skip the D block for a minute. Okay, skip all the way over to here. Group 3 is going to make a +3. Okay, if aluminum loses 3, it looks like neon. Now, let's look at this group here. Okay, this is group 14. Okay, or you could also call this group 4A. Remember, there's like an A and B notation, so this could be 4A. Everything in this column is plus or minus 4. It's kind of the halfway point. If you look at carbon, if it loses 4, it looks like helium. If it gains 4, it looks like neon. Silicon, if it gains 4, it looks like if it loses 4, it looks like neon. If it gains 4, it looks like argon. Remember when we're talking about our valence shell, we're talking about the S and P electrons. So if you look here at gallium, for example, people start thinking, wait a second, it has to lose all of these to look like argon? No, we're just looking at the S and P orbitals. So it gets a little bit weird down here. So that's why it's nice to just focus on the columns. It's a little more straightforward. Okay, group 5A or group 15, depending on the number system that you like to use, okay, is going to make a -3. Nitrogen's going to gain 3 to look like neon. That's going to be easier than losing 5. Okay, so everything here makes a -3. The oxygen column makes a -2. The fluorine column makes a -1. Noble gases, no charge. Neutral. Already stable. Don't want to be messed with. Okay. Now, let's look at this weird D block. The D block. groups 3b to 12b, right? That weird B section of the periodic table. This is the part that always breaks the rules. We say that they can have a variable charge. There are lots of options. You can have iron 2, iron 3. You can have copper 1, copper 2, right? There's different charges that can be made. So what that means is you need more information. You have to be told what they're going to do, okay? There are a couple that you need to memorize because they do not have variable charges. This little cluster in the corner over here. Zinc will only make a +2. Silver is a +1. Cadmium is a +2. You need to memorize these because there's not going to be information given to you to figure it out. The rest of the D block you'll figure out with something I'll show you in a minute, but these three you will have to memorize them. Let's look at how we name something that's ionic. We're going to put the cation and then the anion. We're always going to follow that pattern. If it is monoatomic, you just list the name. Okay? The anion is going to be a little bit different. You're going to have the root of the ion or of the atom, and then you're going to change the ending to "ide." So you don't say chlorine, you say chloride. Then you kind of smush these things together. You have the cation, you have the anion, you smush them together, you get calcium chloride. Okay? So the key here is this ending part. And once you hear them a couple of times, you'll get used to it. So for example, fluoride, chloride, bromide, iodide, oxide, sulfide, selenide, nitride, phosphide, right? So you kind of hear that pattern where you change the ending to "ide." When you see that, right, you know that it's not an atom, it's now part of this compound. Polyatomic is nice because you're just going to keep their normal names. The not so nice part is you have to know what their normal names are. They have these special names that you memorize. So you don't have to change them, but you do have to know what they are. Okay, so this is potassium. It's the cation, so it's going to stay the same. This I've memorized, and I know that PO3, 3-, is phosphite. So this is potassium phosphite. If this was PO4, it would be potassium phosphate. So some of the names are very similar, so be careful that you don't, mix them up. Naming things with variable charges in that D block, you have to use a Roman numeral, okay? It's going to require that you do a little bit of puzzle solving and you kind of figure out what the charge is. So, for example, this is lead, this is chlorine. I changed the N to say chloride, so it's lead chloride. But if I only tell people lead chloride, they have no clue which version of lead it is. So what you have to do is you got to figure it out. I know that chlorine makes a -1 because of its position in the periodic table. There are 2 chlorines. So I have a total of a -2 here. So to balance that out, the lead has to be a +2. So I'm going to use Roman numerals and I'm going to tell people that it was lead 2 chloride. Here we know that oxygen is a -2. So to balance that out, this has to be iron 2. So this is iron 2 oxide. It needs to be in parentheses, it needs to be Roman numerals, and it needs to be attached to the cation part. If you forget the Roman numerals, it's wrong. So be very careful. Okay. So let's do this example. We're trying to figure out what the charge would be. Well, this is the cation, this is the anion. I have 3 of these chlorides. They each come with a -1, so there's a total of a -3 here. So to balance that out, the iron must be +3. So this is iron 3 chloride. Not always so easy, okay? Sometimes it's a little bit more like a little algebra puzzle. So we know that nickel is my cation. We know that nitride is my anion. I have 2 of them. They each come with a -3, so that's a total of -6. To balance it out, the 3 nickel atoms are going to have to cancel that -6 charge. So in my head, I have to figure out, okay, 3 times what is going to give me +6? Well, 3 times 2, right? So if I have 3 nickel atoms that each have a +2, they will be able to cancel out those nitrides. So this is nickel 2 nitride. Let's do covalent next. Covalent is so much easier. You have to memorize a couple of things, but it will be much easier than these ionic ones. So for covalent, you're going to have typically those nonmetals bonded together. Things are going to keep their normal names, except you're going to change the very last element to "ide." The thing is, because they don't make ions, you have to tell people how many atoms of each thing you have. There will be no puzzle for them to solve, like on an ionic. They cannot work backwards and figure out how many you needed. So what we'll have to do is memorize some prefixes. You need to memorize 1 to 10. Those prefixes will tell people how many atoms you have. A small thing to keep track of is that we never say mono for the first element, okay? So if I have CH4, it would be carbon tetrahydride. I don't say monocarbon, okay? You can say mono if it's the second element or the third element or the fourth element, but not if it's the first one. Another thing to look out for are double vowels. Double vowels are sometimes okay and sometimes not okay. So any double vowel with I present is okay to leave. So diiodide, totally fine. Pentaiodide, totally fine. Monoiodide, totally fine. Monooxide, nope, not okay. Do you see how the double vowel here does not have an I in it? What you have to do is you have to drop it, okay? So you're going to drop the vowel from the prefix and then smush it back together. So you don't say monooxide, you say monoxide, okay? That is a common mistake. People forget about their double vowels. Let's do a couple practice. P2O5. Well, I have 2 phosphoruses, so that'll be a prefix of di. So I say diphosphorus. There are 5 oxygens, so I say penta. And then I don't say oxygen, I say oxide. And then I check for double vowels. I don't say pentaoxide, I say pentoxide. So diphosphorus, pentoxide. You can see I got rid of the A here. We don't want that. I don't say monocarbon, I just say carbon. And then I say di. I don't say oxygen, I say oxide. Carbon dioxide. I don't say monocarbon, I just say carbon. I do say mono here for the oxide, but because of the double vowel, I'm going to drop one of them. It's going to be carbon monoxide, not monooxide, monoxide. Next, there's 2 nitrogens, so that's dinitrogen. There's 1 oxygen, So that's mono, and then oxide, and then I drop the double vowel, I get dinitrogen monoxide. Naming metallic substances is super easy. You just say the name of the metal. That's copper. All done. You say iron. All done. It's because they're neutral, right? When they're neutral, you don't have to give any other information. There's no charges to figure out. You don't need Roman numerals. It's just a chunk of metal, right? It's a chunk of neutral metal. Another little odds and ends that you need to know is diatomic elements, okay? Diatomic elements are things that come as a pair. They don't come by themselves. We have a mnemonic. Horses need oats for clear brown eyes. Eyes is in quotations because it's not quite gonna work. You'll see why in a minute. The H stands for hydrogen. The N stands for nitrogen. O is for oxygen, and then fluorine, and then chlorine, and then bromine, and then the I stands for iodine. Okay, so that's why this one doesn't quite work. These elements naturally come as a pair. You are not going to naturally have hydrogen as a single atom floating around. You're going to have it bonded to another hydrogen. So if I say hydrogen gas, you need to know it's H2. If I say chlorine gas, you got to know it's Cl2. So these are diatomic gases. Sometimes people will refer to them as H7 because there are 7 of them. You have hydrogen, and then the other 7 start with nitrogen and form the shape of a 7 on the periodic table. And nitrogen's atomic number is 7. So H7 reminds you that it's hydrogen, and then you have nitrogen, oxygen, fluorine, chlorine, and bromine, and iodine. And they make a little shape of a 7 on the periodic table. So I am sure that I am missing something. There is always some weird naming exception or some random, rule that only applies on this one element every other Thursday, right? It's kind of, the rules are always so wacky. So I'm sure I'm forgetting something, and that's the reason we do our practice. So when you're doing your practice worksheets, when we come across something strange, we're going to add a note to it. We're going to annotate it. We're going to use our worksheets as little extensions of this lesson. If I were to sit here and try to teach you every single naming rule possible, we would do nothing but this until June, okay? There are entire textbooks that are just naming rules. It's crazy. They're like inches and inches and inches thick. So in my experience, having done this all these years, if we have these basic concepts down, we can get decent at the normal ones. And then when there's a weird one, we'll just take a little bit of notes on it and we'll add it to, to our annotations. Okay. We're going to do some practice together, in class as a group, in addition to the worksheets. Please make sure that you are engaged and you are trying them. Practice makes perfect, especially for naming these things and writing formulas. It's very, very important to get that repetition because you got to be able to do it quickly. You can't spend 3 minutes naming one molecule or you will never finish anything, okay? So memorize your common polyatomic ions. Make sure you know how to use the periodic table to find your charges. Make sure you have your prefixes and your diatomic elements memorized, right? Get those basics down, put the time and effort into them, and you're going to be way more successful the rest of the year. Okay? All right, everybody. I hope that's helpful. Bye.